Hi, good morning, everyone. This is Ali Rasek. I'm a structural engineer with HDR, and this is July 19 class for Civil 459. So hopefully you guys all finished the test. It was planned to finish at 11:30 if there was no glitch, no Microsoft issue or similar. And yeah, just raise your hand if there is any issue. Otherwise, I continue. I think you have finished. Okay, yeah. I received no notification, so probably everything is okay. And okay, let's continue with the teaching for today until about 12:20. So this is the outline. We go through it every time. We are really trying very hard to get to the end of steel design. And then I will have a quick session about concrete and wood. This course is already, it's like a graduate course. It has so much content. So thanks for your patience. It will be fruitful. You will benefit from listening to all sorts of things or just gathering the documents and documenting for yourself. If you work as a structural earthquake engineer, those material will help you in your work. So thanks for attending the class and the report writing and quizzes, etc. Now going to the modules and date. So we are already July 19 and the reports are submitted. Thanks a lot. They are even marked by Behnam. All of them look very good, but I will review and then publish them. And is anybody waiting? It's waiting. No. Okay, good distraction. So they look very good. I expect you guys to submit. So because I want everyone to have equal amount of time. So you submit your presentation by next Tuesday evening, and it has 10 the presentation slides basically. You submitted, and it has 10 marks out of 100. So do a good job on that one as well. And then we proceed with the presentations. So the first set of presentations will be next Friday, 26 July. I will be at campus, and this is a class between 11 to 1:50. I will send an email telling you the location, etc. Yeah, like I chose it randomly. I used the random number generator, but they appear to be all like at the end. The first two teams ended up being in the two sessions. So in a way, maybe appears to be just reverse, but whatever. That's a good plan. We will have teams 3, 4, 5, 6, and 7 presenting next week, and 2 more teams presenting the following week. Now, because I had a trip and I missed one session, I'm trying to do a makeup on Tuesday, same time. However, Tuesday class is not mandatory because we previously said that Tuesday class really won't happen. It was not supposed to, we were not supposed to have a class before 26 July. So yeah, not mandatory. Even if a few people show up, I will just complete the class and record it and upload it for you. That's totally fine. And yeah, so if there are questions about any of these items, please email me or raise your hand, etc. I think it's pretty clear. And we're doing very well, actually, generally in this course. Now, yeah, so if there's no immediate questions, I will continue with see something here. What is the expected length for the project presentation? Oh, yeah, thank you. Thanks for asking this. I was thinking that I missed something. I will write it to you as well. So for every presentation, I'm considering 25 minutes. And so let's assume 25 minutes total length and 5 minutes rest per presentation, or like per every 2 presentations, we'll have 10 minutes rest. At that 25 minutes, you guys present for 20 minutes, and then 5 minutes question and answer by me, Behnam, and everybody. Everybody in the class can ask questions for about 5 minutes. I say about, I will think, I don't want to miss anything, so it's presenting, question and answer, yeah, and then we write down our notes, Behnam and myself, and then we will decide about the marks. Yeah, don't worry about the rubric. It's a little bit like voting. It will be like voting between me and Ben. So yeah, we cannot really make it rubric-y too much. So like I would say, I think it's excellent, and he would say, I think it's excellent, and it's 10 out of 10. Is it more than 10? Yeah, 10 points. So there's 10 points there. Or I say it's good, and he says excellent, and I would say, I don't know, 9 out of 10. Yeah, just try your best. But if I could think about a rubric, I would write it down. But I think right now, or that's what I did last year as well. Last year there was 3 of us, so it was more like voting or between me and the TAs, yes, discussing and then voting and then agreeing on some mark. But yeah, so that's the most important issue is 20 minutes talk presentation by you guys, and then 5 minutes of questions, 25 minutes total. Is it good enough? Was it enough answer to your question? And I will write this down in an email as well. Okay, yeah, thank you. I think there's no more questions. Let's see what we can do about STL. I think we finished this. That's what I remember, but I still opened it to see if there is anything I want to re-emphasize. No, it's mostly the procedure for STL. Yeah, I mean, even to me, sometimes I think that doesn't exactly go with your engineering judgment. But if you think carefully, you will see that we are protecting some members while allowing some other members to become ductile. So this procedure is designed to have some members, that can minimize this, to have some members yield and provide ductility, and every other member to not yield. And another intention is that we do protect some members is that, say you design for earthquake level A, because of what we know about earthquakes in Victoria is like Kaldetskaya level A, and then we know that we looked at the experience in Turkey, and it's possible that the earthquake that really happens is like 50% more, and we want to be at collapse prevention or like life safety, like you want to safeguard lives. So you have gone through all your design based on earthquake at some level for Victoria, let's call it PGA-A, and then the actual earthquake is 50% more. So this lateral load is 50% more, and it's pushing the structure sideways. With capacity protection, we are confident that the weak link in this system is your bracing. So the bracing is the weak link, and the demand is high. Therefore, the bracing will keep on yielding, and the deformations would be higher than what you planned for or designed for. But the vertical load carrying system will still remain intact because you have done capacity protection. Everything else is stronger than bracing, and the weak link in your chain. I don't know if I showed that chain one more time. I have shown you that chain in the previous presentations. So you can think about your load path as a chain, and then you have this, and the load starts from here, goes through the beam and connection. Don't forget, connection is the part of the load path, and to the bracing and more connections and the foundation. And going through this procedure, you have made sure that the weak link, the member that fails, is the bracing. And therefore, when an earthquake happens that is unusually high, more than the design, what the code has provided, or what the scientists and geologists expected, still your braces are yielding and everything else remains intact, which is very important in our philosophy of design. So yeah, it takes time for it to settle, but you will appreciate it, like when you practice it, maybe do some exercises, etc. You will appreciate its concept. Especially think about earthquakes that are greater, larger than what you designed for, and the fact that the structure won't really collapse in a brittle way after that earthquake. You will appreciate this solution, that this kind of ingenious, smart solution that is provided for earthquake structural engineers. Now let's see if we can go through this example, which is same thing, same scenario, but with some numbers. So basically, we have a brace system, again, concentric. They are meeting at the same location. There is no shear zone in between. And the base shear was calculated to be 135 kilonewtons. And this number is already a reduced number, which was based on a ductility reduction factor of 3 and overstrength reduction factor of 1.3, which you multiply them, it's like 4 times lower than the what you see from the PGA, or sorry, from the spectral acceleration. So that those procedure has been done and the reduction is applied, and you are designing for 135 kilonewton. Shear load already includes accidental torsion, so don't worry about that part. And need to add notional load, 0.5% of the total gravity load for each story is added for accidental torsion. These loads are to account for the stabilizing effect of gravity loads. Like maybe these vertical members are not completely perfectly vertical, or like the profile that you are using is not exactly perfectly straight, and therefore there's a random eccentricity. Basically, that's all what notional load is doing. So you apply the side load, which is 5% of the, sorry, 0.5% of the vertical load, gravity load, to account for that phenomena. So this is added. For this example, gravity on the bay is 1,000 kilonewtons. Hence, notional load is, we said, 0.5%, which is 5. So you add that effect to your seismic load as well. 135 plus 5 is 140. For the capacity design, use the capacity design forces from the yielding elements and do not include the notional load. So that's the procedure. Apparently, okay, we did this calculation. We applied the 140, exactly 140, like which is the demand. And then we calculated, or maybe SAP 2000 model or hand calculation based on this equation here. You get a load of 116 in the bracing. And this bracing is in tension. This one is in compression when the load is in this direction. However, we know that an earthquake could happen in both directions, so we should always have this in mind that the load goes in both directions. This is a symmetric system, so we can continue just knowing that everything will mirror out. And so axial resistance of the braces. So basically, we can design these two braces just for 1/16. But for every other member, we don't use the result of the analysis. We have to go through that capacity protection procedure because the rest of the members are capacity protected. We calculate the axial resistance of the braces. So we go through the procedure of the buckling load for compression. That's the procedure is here for Euler buckling load or post-Euler buckling stress. And basically we can find we can size the members. So brace load was 1/16 kilonewton, length was 5,000 millimeters, 3,000 and 4,000. The total is this length would be 5,000 millimeters. And so that we have the length, and we use K equal to 1 because it's like pin on the two sides. More normally, most braces are pin, except that there is a special condition, but brace, we normally think about it as pin. For two reasons. One is that the connection is pin. So give me 1 second. Okay, yeah, not very important, sorry. So the two reasons that we think that the braces are pin. One is that like the connection is pinned. The other is that normally the braces are so weak that they cannot, like in bending, they are weak, so they cannot really take bending. So even if the connection appears to be strong, but the bracing cannot take bending, so practically it acts like pin, and therefore K equal to 1 is a good assumption. Now some selections, we could use like HSS 89 times 6.4, thickness of 6.4. Just use your handbook. So you see that this is a pass, which will provide 140 capacity, and the other one, 102 by 102 by 3.2 thickness, provides capacity or in compression of 118, and both of them are greater than 1/16 that we calculated for braces. Therefore, either one could be used. And so you want to be very economical, you use the one with the smaller area, which appears to be the second one, like just to not use, like to be economic on expense or not to be wasteful, etc. That reason, but okay, sorry, I should also add that with capacity protection phenomena, like procedure, if you're bracing, you choose it to be too strong, then in order to capacity protect the other members, you should also make them too strong. So it will have a effect on the rest of the design. So that's normally we don't have that in typical structural engineering, like we just independently make any member strong enough. But in this case, there is a feedback effect, like if the ductile member is too strong, then it will cause the other members to become too strong because of the procedure that we are following and the intention that we have, that the weakest link being these braces. So don't make it too strong for a few reasons. One is the canonical, and the other one is this earthquake engineering concept that prohibits making it too strong. Actually, we want it to be weak. Remember that we reviewed this idea a few times, that sometimes weaker is better in earthquake engineering. That's one of the cases. And now we should back calculate the probable capacities. So we had the capacity, like we have the capacity of that member, those members in compression. And now we want to have the probable capacities. And as you have probably seen in your steel design course, you know that like one member is in compression, the other member is in tension, and compression controls. So compression members are weaker in compression. Therefore, that's why we only designed for compression. Otherwise, by book, we are. Otherwise, if you want to go by the book, we should, like prescriptively, we design both of them for tension and compression, but we know that they are going to be weaker in compression. So that's why we only did compression. That was the only reason. You checked it for tension and it would be a pass. Now go for the, now that we have sized the bracing, the ductile part of the system, now let's find about their probable capacities. First, find the resistance of the members in tension. So axial tension, is it to calculate? You don't necessarily need to use the tables. It's phi cross area, Fy, and for HSS 102 by 102 by 3.2, the capacity, the tension capacity is calculated to be 387 kilonewtons. That's, as we rightfully expected, it's much greater than the compression capacity. So tension capacity is 387 kilonewton, but the other brace with buckling compression line before then. Yeah, so, and then this load reverses, so both of them should be designed similarly. Now that we have the tension capacity, let's go for the probable tension resistance, tensile resistance, the same member, and we have its compressive capacity, area, and tension capacity, and we compute Hg, Ry, Fy. So here you see that we have Ry, which is increasing the value instead of phi, which reduces the value. And there is a minimum for Ry, Fy, which was 460 megapascal for HSS, so we use 460. And we see that the probable tensile capacity would be calculated to be 566, larger than 387. And we already looked at those curves of material property. We know that for a structural, we used like a safe value for material tensile capacity, while the probable value is greater. So that's why we go through this procedure to find the probable value, which is quite a bit larger than the design value. Probable compression resistance. Again, I showed you the equation last time. And so you go through the procedure, just replacing phi Fy with Ry Fy. So maybe you can even calculate the ratio or just go through the whole equation, and you see that probable compression would be 164 kilonewton, and while the design compression was 118. So we have a larger value here as well. But but maybe that member is already buckled, so we want to estimate its post-buckling capacity. So how much resistance it shows after it's already buckled. And so there was this equation multiplying 20, like multiplying by 20%, multiplying the tensile capacity by 20%, and you get a value of 113. So during the earthquake, we can assume that, so we have calculated all these values, the tensile capacity for design, compressive capacity for design, and then probable tensile capacity, probable compression capacity, and what if the compression side is already buckled. We have provided all these values, and now we proceed with the capacity design. Basically, we assume that this member is at its probable tensile capacity, and this member is at its basically probable post-buckling capacity, and which is 113, and this member is, or at its compressive capacity, I guess whichever is greater. So if this member is saying 162, maybe it's not buckled because we don't know. This member is at 566, and we do basically map them into the horizontal direction, back into the horizontal direction. So we are now back calculating. We are back calculating what other members will see when these members are at their probable capacity. This member will exert an horizontal force of 341, and this member will exert a compression force of either 97 or 68. And for each of these two scenarios, whether it's post-buckled or it's not buckled, we can calculate the total horizontal force applied on the system. It's either 438 or 409. So it's much greater than original load, or greater than the original load, which was 140 kilonewton. So your earthquake load was 140 kilonewton. However, for capacity design, you have a larger number here. Again, comparing the two, maybe I should have put it here for comparison. So every other member, which is capacity protected, will be designed based on this load. You can apply this load to your SAP 2000 model or frame, etc., and read the forces in beam, in column, in the connections, and design everything else for this load, except for two members, brace 1 and brace 2, which are already designed. So you don't change the design for brace 1 and brace 2, but you will update it for everything else. So implications. Design connection for tension of 566. Design force was 116 kilonewton. So the ratio is 4.9. Foundation uplift is very large. Column loads are high. Diaphragm and rest of the structure has high forces. However, per class 2712, I think I remember that we read it through, the limit for capacity design forces is like a modification factor of 1.3. So we don't really need to go, that's like a ceiling. We don't need to really go beyond that. And what does that mean? Our initial load was 135 using the RDRO of 3.9. Now, if we are using a RDRO of of 1.3, then the load is only 405. And then you add your notional load to it, that would be 410. So 410 is slightly better than the numbers that we are seeing here, right? It's better than 438. So the final conclusion going through this procedure is that design everything else for a load of 410. So that clause here did a little bit better, like 5% better than designing for 438. But I have seen scenarios where it helps a lot, because basically I really highly recommend to go through this exercise. And we have two options. The only change that you guys make is, instead of using option number 2, HSS 102 by 102 by 3.2, use option number 1 with a larger area, and then you will see that your probable capacity of bracing is also increases. Like these two values, these three values, the probable capacities also will increase quite a bit. And then these loads will be much larger, like say order of 600 kilonewtons. And then you will really feel the saving by this upper limit, because your upper limit is really 410. So you don't need to design for any lateral load greater than 410. Then you will really feel the benefit of this ceiling that the code has provided. And the reason is that exactly that. Like I have been in those scenarios where like engineers have over designed the lateral load system, and therefore when you go through the capacity design, you end up with, in a way, astronomical values for capacity protection. But luckily the code has provided an upper limit, and therefore you don't need to use astronomical values. You just go up to the value that says I almost have no ductility. So there is nothing beyond that. You have no ductility, no reduction factor. Okay, Chad came in. Even the tension force will not happen. Let me see. Even the tension force will not happen. We need to design with it. If you mean the tension force in bracing, if you want to open your mic. So don't forget that in first step, when we put a ceiling, that's a ceiling for everything. However, just want to reiterate this issue that for lateral force resisting members, we use the 140, which was out of your SAP 2000 program. And in a way, that chapter of design is finished. So we don't think about it anymore. So those members who are in charge of carrying lateral loads, they are designed and they are finished. And we are within the step where we are capacity protecting everything else. And yeah, so you said that maybe your question is that when we when we use the other member, the tension capacity also increases. Like the area is larger, therefore the tension capacity is larger than this TR that we are seeing here. And based on a structural engineering mindset, it's a pass because the capacity is more than demand. So we say it's pass. However, the but the effect it has on the design of everything else is that the tension capacity would be larger with that other profile. The capacity would be larger with the other profile, but we don't mind generally. But then the probable tension and probable compression capacities go larger And when we want to back calculate these values that are applied to capacity protected members, they are large and they make capacity protected members enormous. So if I am that, yeah, if I understood correctly, yeah, you were asking if the tension capacity increases, yeah, the larger profile will have larger tension capacity. Did I answer your question? Okay, yeah, sure, yeah. So, yeah, don't expect too much from yourself or me. Like this procedure is confusing to everyone, but including me. But I think carefully, it's very smart. So I'm happy with it, but I sometimes might even explain it myself. Yeah, that made it slightly confusing, but it's a good procedure. I guarantee that. So we were here and we said that there is a ceiling to the value for capacity protection. Capacity design forces. Assume compression brace is at the probable post-buckling resistance, but distribute the rest to the tension braced. VT slightly increased, but the probable tension almost the same after all. So yeah, so that's just summarizing what we were talking about. And there is a capacity of 570 and 113 in compression after all. Any questions? Any more questions on this slideshow? Yeah, I very highly recommend that. Like if you didn't do it for the rest of the course, but for this particular slideshow, just go through it a few iterations, even criticize it until you fully understand this procedure. Because I like it. It's a nice procedure, and it's generally designed in a smart way. Let me see if I can start the next slideshow. That order. So there were quite a few examples, but I call this the next example. We have this in SAP 2000. Let me see, didn't we have a 2D model as well? Yeah, this is 2D, but that's pushover. That's reiterating pushover. So we will go through that one as well. And then the still section will be finished. But I think part of that I will be doing in that recording that I will create next Tuesday. And as I said, you are welcome to attend. I will go online. Everything will be the same, except that, I mean, it's not mandatory because it was not in your original schedule. So maybe you have planned something else. Maybe, yeah, you don't want to, that's fine. The recording will be there. So let's continue 10 minutes. I just explain the situation here. This one, we try to make it more real. This is a 3-story brace frame building designed based on National Building Code of Canada 2020 and Canadian Standard Association S16 for steel, steel design. This is a moderately ductile chevron braced frames for seismic force resisting systems. So you have a chevron, basically concentric bracing, and so effective seismic force procedure and response spectrum analysis in SAP 2000 is used to get the forces and check the design. You are familiar with both procedures. Modeling mass. So it is key to correctly model the seismic weight to get the correct base shears, especially for RSA. You know that dynamic analysis is dependent on the masses. Add the mass to the model in horizontal direction because you don't want it to be confused with the weight. So a lot of times we only apply it only in the horizontal direction, or I can say horizontal direction is very important. Vertical, you should be careful not to add to the weight of your structure by adding mass in vertical direction. Add either joint, line, or area mass, depending on your program and level of accuracy that you want, or adding dummy elements with no stiffness and only mass, similar concept as cladding. I know that these days people want to do it more sophisticated way, but I would have been happy just to add it as nodal masses. Units, yeah, units is always key. Like use the correct units and uniform units, whether it's kilograms or meters, etc. And then in the industry, even in Canada, there is use of inches and feet and pound force and the unit of mass in the US system or the imperial system. It's even more confusing, so be careful with those values. Units are the number one source of error in a lot of analysis. Analysis model, the SAP 2000 model is initially comprised of W310 times 39 beams. I will share the model with you if I hadn't already done that. Those are the beams and columns. Beams and columns are W310 times 39 and HSS 203 by 203 by 6.4 is used for bracing. For simplicity, in the SAP 2000 model, we assume 150 millimeter concrete slab for the floor and 25 millimeter for the roof, connecting all points in each level using a diaphragm constraint. In reality, there is a little bit of flexibility, especially roof, because you see that the roof is thinner. But the assumption in the model is that it's a very stiff roofing system and floor system, and all nodes move together. 25% of the snow load should be added to the roof per National Building Code of Canada. Therefore, using 1.5 kilopascal for snow, and total roof area is 648 square meters. Therefore, adding 243 kilonewtons of snow on the roof. For seismic cases, add as weight to roof joints. So I guess like there are 35 joints, 7 kilonewton on each joint in the horizontal direction only. For snow load case, add as area pressure at 1.5 kilopascal to level. So you do it separately. When we are doing it separately, you don't want to do it twice. Therefore, you add it as load or pressure. And then, because at the same time you want to add the mass, in order not to do it twice, you add the mass only in horizontal direction. At least that's the old school way that we do it. Maybe more modern programs can handle this issue better. Analysis model add 50% of live load and partitions to the first two floors. Therefore, 3.5 kilopascal for live added to model as area pressure on level 1 and 2. For partition, use 1 kilopascal for partitions, and the value is calculated. For seismic cases, model as horizontal loads, but only need 0.5 kilopascal. Add as weight to floor joints. For dead load, model as area pressure and use 1 kilopascal. So that's the process. And similarly for cladding, add 1.5 kilopascal for cladding on the floors. 1 and 2 include 2 meters below and 2 meters above. So you want to basically account for the walls as well, or like up above the floor and below the floor, half and half goes to that floor. Roof only consider 2 meters below because obviously there's nothing above it. Model has area sections with mass but no stiffness. So that's the way we included it in the model. But as I said, nodal mass would have been good enough. Modeling consideration to check seismic weight. First, compute the dead load case before you add additional masses. So basically, it's sanity check. You should do sanity check on your models. Double check the total weight with the weight that you are reading from the model, reaction that you are reading from the model, and make sure that you have done it correctly. And then you add the masses and apply the horizontal static acceleration case scale to 1. Calculate the base shear, should match what you calculated by hand. So those are sanity checks. Since the requirement from National Building Code of Canada is that the seismic force resisting system must be designed to carry 100% lateral load, we need to change the frame condition to pins. Otherwise, there will be moment frames acting, which will reduce the forces in the frame. So basically, what we are saying here is that if your design is for bracing to withstand the lateral load, make sure that your model is also the same, and your model is not a moment resisting system which withstand the lateral load, because you don't need you are not intending to design as such. This should apply to beams and columns. Beams and braces, while columns can remain continuous, and then they won't really attract lateral load. This is done in SAP 2000 by changing the frame element and fixity release, set the moment in mode access to release. So that's the technicality of how to do it. Modeling considerations: actual diaphragms should likely be composite steel deck concrete slab. This could be modeled with area elements with adjusted stiffness and density, or using sets of beam elements. Many designers would use ETABS, which incorporates composite deck elements. So I have almost zero experience with ETABS, but probably you guys know better. Okay, I think that's where we can end the class. I am waiting for your questions. Otherwise, yeah, have a very good weekend. And I will send you a few emails about what is coming up for us.
Hi, can you hear me?
Yeah, sure. Yeah, hi, Griffin.
Hi, so we're in group 2 for the project presentation.
Okay,
and
yeah.
We have a member that had something planned for the August 2nd, Friday. So we're wondering if we could get moved to the 26th.
Sure, yeah, group 2. Okay, yeah, be ready next week.
Okay, awesome. Thank you very much.
All right, yeah, thank you, Griffin. Thanks a lot. I close this. Yeah.